Okay, so today is all about 2.2 polynomial functions, and we're going to be spending 2 days on 2.2. So the first part of it today is being able to find the maximum number of zeros and turning points in a polynomial, which hopefully sounds a little bit familiar from advanced algebra trig. And then using the leading term test to determine end behavior of a polynomial. That one might not sound as familiar. But it's a fairly simple rule to follow. And when all else fails, you can always still graph it. But yeah, so go ahead and grab your notes and let's get started here. And that's my water bottle cap. (2.2) day 1, polynomial functions. All right, so 2.2, and actually I believe 2.3 as well, and maybe even 2.4, continue going deeper with polynomial functions and what we can do with polynomials. So first off, we have to kind of define what a polynomial function is. So it's any function that can be written in the form f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1. And this notation here is just something to index it with. So you could go a, b, c, d, e, f, or you can index it as a sub n minus 1, and so on and so forth. Plus dot, 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 plus a sub 2x squared plus a sub 1x plus a sub 0. Okay, so any function that can be written as basically a bunch of added together x to some power is a polynomial function. N is the degree of the function. And it's the highest power of x. And then a sub n is called the leading coefficient. Okay. So we can use the degree and the leading coefficient to tell us a lot of different things about our polynomial. So for example, if we were asked to just find the degree and the leading coefficient, we had f of x equals 4x to the 5th plus 7x squared plus 9x plus 2. We had something like that, and we were asked what is the degree? Well, the degree is the highest power of x. So that would be 5. And then the leading coefficient would be 4. So it's all based around that highest power of x. And even if it wasn't written in quite the right order, you would still want to go through and find whatever x has the highest power. Typically, it's supposed to be written in descending order of powers of x, but occasionally, like the book or something might throw a problem at you where they wrote it in a different order just to see if you could remember, oh yeah, it's supposed to be the highest power of x or whatever. So yeah, that's one type of question we might be asked. So being able to identify the degree and the leading coefficient is important for this next part, because this next part introduces something called the leading term test. Leading term test. Okay, So the leading term test is something that you can use to determine the end behavior without graphing the polynomial. Okay. So let's suppose we have this polynomial f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 a sub 2 x squared a sub 1 x plus a sub 0. So let's say we have this polynomial here. The thing that we're going to be looking at is this leading term right here. So this is the leading term. It has the leading coefficient and it has n for the degree. And so there's a few different things that this can tell us. The first option, if a sub n is positive, and n is odd, then it tells us something about the end behavior. It tells us that the limit as x goes to negative infinity is negative infinity, and the limit as x goes to positive infinity is positive infinity. So the idea that we get here, or an example of what that might look like, is if we had something like y equals x cubed. So our leading coefficient is positive, n is negative, and we have the right-hand side going off to positive infinity, and we have the left-hand side going off to negative infinity. So that's an example of this first case here. Okay. The second case, if a sub n is negative and n is odd. So that would be like the case if we had y equals negative x cubed, because the leading coefficient is negative and n is odd still. And so that function, y equals negative x cubed, looks like this. So we can see as x goes to negative infinity, f of x, the function, or goes to, sorry, not negative infinity, positive infinity. And then as x goes to positive infinity, f of x is going off to negative infinity. So it's kind of the opposite case of the first one. Then we have two more cases. The case where it's even and positive or even and negative. So if a sub n is positive and n is even, we have the limit as x goes to negative infinity and the limit as x goes to positive infinity of f of x. And this might be the case of like y equals x squared. Where they're both going off to positive infinity. And then the final case, if a sub n is negative and n is even, and this might be like the case of like y equals negative x squared. So it's just a flipped parabola. And they both end up going off to negative infinity. Okay. So those are kind of our four options here using the leading term test. So this is a way that we can figure out end behavior of a polynomial without having to type the entire thing into Desmos, without having to graph it on a graphing calculator of any kind or graph it by hand or whatever you like to graph with. So it's just kind of a shortcut for us. And you can always graph it to check yourself and make sure you've got it. But this test works every time for a polynomial. Okay. Any questions about the leading term test or how we might use that? Okay. So the next thing we're going to talk about is zeros and turning points. Different color here. Zeros and turning points. So we can also use the degree of a polynomial to tell us the maximum number of zeros and the maximum number of turning points for the polynomial. All right, and remember, zeros are when it crosses, when the function crosses the x-axis. So the maximum number of zeros for a polynomial is equal to the degree of the polynomial. So for example, if I had a quadratic, well, y equals x squared only has 1 0, right? But if we moved it down and we did like y equals x squared minus 3, we would have 2 zeros. So you can, for a quadratic, you can have no zeros, 1 0, or 2 zeros, but 2 is the maximum number of zeros. Okay. So whatever the degree is, that is the maximum number of zeros that you can have. And then for turning points, it's a similar deal. All right. So let's take a look at turning points here. If I have a second degree function, we have one turning point here. If I have a third degree, well, third degree has a maximum number of 3 zeros. So 1 0, 2 zeros, 3 zeros. And on this third degree, we have 2 turning points. Oh, yep, sorry. All right. on this third degree, we have two turning points. It's where it stops increasing and starts decreasing, or stops decreasing and starts increasing. We have two turning points there. And let's look at a fourth degree. A fourth degree can have a maximum of 4 zeros, so let's show something like that. 1, 2, 3, 4. And on this fourth degree polynomial, we have 3 turning points. So we can kind of start seeing a pattern here. The second degree has 1 turning point, the third degree has 2, the fourth degree has 3. What do we think the pattern is here? Anyone see a pattern? Yeah, -1 from the degree. Yeah, so this is our maximum number of turning points. So it's degree -1. That's our maximum number of turning points for the function. Okay. So we've talked about zeros, we've talked about turning points, we talked about kind of the maximum number of zeros. The last thing I want to talk about real quick is the multiplicity of zeros. Okay. So sometimes there's a case in your function where it touches the x-axis and then continues in the positive direction. So it touches the x-axis at a turning point. When it touches the x-axis at a turning point, that zero counts for more than one time of being a zero. It's kind of what multiplicity is. So it's but it's better expressed in an equation. So if I had something like f of x equals x times x minus 1 times x minus 4 squared. This is what multiplicity of zeros looks like in an equation, where you have a repeated zero here, because this is really x minus 4 times x minus 4, right? So x minus 4 shows up twice, so 4 shows up as a 0 twice. So we would call, if I was asked to find the zeros for this polynomial, the zeros would be 1, 0, forgot that one, 4, but 4 would have a multiplicity of 2, because that's how many times it exists as a zero of the function. 4 has a multiplicity of 2 is what we would say. If it was a cube there, it would be a multiplicity of 3. If it was the fourth power there, it would be a multiplicity of 4, and so on. And you know, multiple zeros could have multiplicities on them. So if I had x minus 1 squared or something like that, then 1 would also have a multiplicity of 2. And what it looks like, again, if this was our polynomial and this was 3 right here, looking at it graphically, 3 would have a multiplicity of 2 as a zero of that function. Okay, So let's take a look at some questions that we might be asked to do today, or some questions like some that we might be asked to do. All right, so the first kind of question that we might be asked to do would be to describe the end behavior using the leading term test. And I'm just going to call it LTT. That looks like L pi. Whoops. Leading term test. So we're going to do f of x equals, let's say, x squared times x plus 4 times 2x minus 1. Okay. So for this one, the leading coefficient and the degree aren't immediately obvious from the function itself. So to figure out what the leading term is going to be, you could go through and multiply all of these things together and then figure all of that out, or you could really focus on the highest power of x from each of those and multiplying those things together, since we know that those will be multiplied in. Either way, we can go, okay, x squared times x is x cubed plus 4x squared. And we know that's going to be times 2x minus 1. So then we're going to double distribute here, and we get 2x to the 4th. And this will be our leading term. So you don't really need to go any further than this leading term, but you could continue multiplying it out if you want to, just to double check that that is indeed your leading term. And it turns out that it is. This is my leading term, 2x to the 4th. So then we would want to describe the end behavior using limits. So x goes to negative infinity of f of x, and the limit as x goes to positive infinity of f of x. And since it is a positive leading coefficient, and n is odd, or sorry, n is even, gosh, positive and even, you can look back at your notes if you need to and remember that the positive and even case is where both ends are pointing up. So we would know that the limit on both of them is infinity. If it helps more to remember the different basic forms of each of these, like x cubed and negative x cubed and x squared, and what each of those ones do, then you can remember it that way, or you can remember it using, you know, the positive and odd, negative and odd, all of that stuff. Either way. But yeah, so that is what our end behavior would be, since we have the case here where a sub n is positive and n is even. So when we need to explain ourselves using the limit, the leading term test, this is sufficient explanation for me, saying that the leading term is greater than 0 and that your degree is even. Okay, so that's one kind of question that we might see. Another one that we might see is let's see, state the maximum number of real zeros and turning points. Then find the zeros. Okay, so we could see something like that with a function like we will do x to the sixth minus 6x to the third minus 16. Okay, so our maximum number of real zeros would just be the degree. And our degree is 6, so max zeros is 6. And then the max turning points is just 1 less than that, so it's 5. And then finding the zeros. You can either factor this thing to find the zeros, or you can graph it. I'll show both. So if we're on Desmos and we've got x to the sixth minus 6x to the third minus 16, it shows us 2 zeros here. One at negative 1.26 and one at 2. And we can zoom out just to make sure there aren't any others that we can see, but there's not. Just these two. All right. So those would be our zeros there. And technically, you would want to say at x equals negative 1.26 and 2. Okay. If we were going to do it by factoring, let's see, does this thing factor nicely? No, maybe. No, this thing doesn't factor nicely anyway. So we'll just show it by graphing. Okay. So there's our maximum number of zeros, there's our maximum number of turning points, and then there's our actual zeros found by graphing. If you find ones that do factor nicely, you're welcome to factor to find the zeros, because I know we all love factoring so much. Or if you have a quadratic, you can always use quadratic formula, things like that. If you want to practice your factoring, go for it. Let's see. And then the last kind of question that we might be asked, we might be given something that's already factored and asked to find the multiplicity of the zeros or find all the real zeros, and things like that. So find all zeros and state multiplicity of any repeated zeros. Okay. So we might be given something that's factored already, in which case that's really nice and easy. We might be given something like f of x equals x minus 3 squared times x minus 1 times x plus 4 to the 5th. And so then our zeros would be x equals 3, x equals 1, and x equals -4. But then 3 and -4 would both have a multiplicity on them. So x equals 3 would have a multiplicity of 2, and -4 would have a multiplicity of 5, since that's the exponent on that one. Okay, so we might have a case like that. We might also have a case where we need to either factor or graph it. So we might be given something like f of x equals 4x to the 4th plus 4x to the 3rd plus, we'll say, let's see, something that would make this factor nicely. Plus 48x squared. Or sorry, minus 48x squared. Okay, so if we had something like this, then we might have to factor it first to figure out the multiplicity of any zeros, or you could also stick it into Desmos and take a look, but just remember to find multiplicity, we would have to have a spot where it touches the x-axis and then bounces away from it instead of crossing it. Okay, anyway, we'll show the factoring way first. So the greatest common factor here would be 4x squared. So we'd factor that out and get x squared plus x minus 12. And then continuing to factor here things that multiply to -12 and add to 1, we'd end up with x plus 4 times x minus 3. So from here, we can tell that our zeros would be x equals 0, x equals -4, and x equals 3. But then 0 would have a multiplicity of 2. And we could see it from graphing as well. We could go 4x to the 4th plus 4x third minus 48x squared. And we would see the 0 here at -4, the 0 at 3, and then we see the place where it has a turning point and a 0 at the same spot. So that's what creates that multiplicity of 2 for that 0. Okay, so that is all the kinds of questions that you will most likely be seeing today on your assignment. Any questions at this point? Did the 0 come from the 4x squared? Yes, it did. That was what we had factored out. And when you factor out something that has a variable in it like that, it does affect the zeros. So to find your zeros for each of these, you would set each of these terms individually equal to 0. And when we set 4x squared equal to 0, the only way that we can get that to happen is for x to be 0. Yeah, so anytime actually that you see something with an x factored out, 0 is going to be one of your zeros? Good question. Any other things that we want to talk about? Any numbers we're not sure where they came from on any of the examples? Okay. We're going to try the poll thing real quick, because that's a new feature. All right. So go ahead and try to find the poll feature. On a scale of 1 to 5, how do we feel about what we've learned so far today? 1 is let's do more examples. I'm feeling kind of lost. 5 is being let's start the homework. And it should be under the poll. So to get to polls, if you haven't had a poll in a class yet, I believe what you do is you go to the chat area, and then there's these 3 shapes. Click on the 3 shapes and then click on polls. All right, looks like most of us have voted, and it looks like most of us are in favor of getting going on the homework. So if that is you, and you're ready to get going with the homework, great. I've just posted it in Google Classroom. It's a worksheet, and you can go ahead and get started. For those of you who are not quite ready to move on and would like to see some more examples, stick around. I will post an exit ticket towards the end of class, so if you leave, make sure you do the exit ticket when I post it. But for those of you who would like more examples, I will get going with some more examples. For those of you who want to just get going on the homework, you are free to go and get going on the homework.